This lesson is about finding the distributions of sums of independent random variables. The first example we're going to look at is a sum of two independent discrete uniform random variables on the set 0, 1, 2 up to some number n. The PMF of x plus y is p of m equals m plus 1 over n plus 1 squared if m is less than or equal to n, and 2n minus m plus 1 over n plus 1 squared if m is bigger than n. So for the proof, first notice that m has to be between 0 and 2n, because x and y are at lowest 0, so x plus y must be 0 at least, and at most it's 2n because x and y can each at most be n, so x plus y can at most be 2n. Also, for x plus y to equal n, x must equal I, and y must equal m minus I for some number I, and that way I plus m minus I equals n. If m is less than or equal to n, then x can take any value up to n, because it can be at most n because y can be at least 0, so it's going to be m plus 0, which equals n. And so the probability x plus y equals n is the sum from I equals 0 to m of the probability that x equals I and y equals m minus I. So we're looking at all possible combinations of x being a number from 0 to m and y being the other number that when added to x gives you m. Since x and y are independent, the probability x equals I and y equals m minus I is the probability x equals I times the probability y equals m minus I. Since x and y are both uniform on the interval from 0 to n, and taking into account that this is actually n plus 1 numbers because it includes 0, the probability they equal any particular number is 1 over n plus 1. So the probability x equals I times the probability y equals m minus I is 1 over n plus 1 squared. Now we're summing that number from I equals 0 to m, which again we have to take into account 0, so that's m plus 1 numbers, and so we get m plus 1 over n plus 1 squared. On the other hand, if m is bigger than n, then x must be large enough so that x plus y can equal m. That is, if x equals 0, there's no way that x plus y could equal m, which is bigger than n, because y is going to be at most n, so n plus 0 is still n, which is too small. And so m is going to have to be at least as big as n minus n, and it could be any number from m minus n up to n. And therefore, the probability x plus y equals m whenever m is bigger than n is the sum from I equals m minus n to n of the probability x equals I and y is m minus I. Once again, we use independence to rewrite that as the probability x equals I times the probability y equals m minus I. And once again, we use the fact that x and y are uniform on 0 to n to write this as 1 over n plus 1 squared. However, now the bound on the sum is different, so we're summing from m minus n to n. And the amount of times we've added 1 over n plus 1 squared is n minus m minus n, this number here, plus 1, because we shouldn't actually subtract off the m minus n, just like above whenever we had a plus 1 for 0. So it's n minus n plus 1, or in other words, 2n minus m plus 1 whenever we rearrange that algebraically. So for numbers m bigger than n, the PMF is 2n minus m plus 1 over n plus 1 squared. So you can see it's a little more complicated than you might at first think, but sometimes it works out very nicely. So for example, if we sum two independent Poissons, if x is Poisson lambda and y is Poisson mu, and these are independent, which is a necessary condition, so that's important, then x plus y is Poisson lambda plus mu. And I think this works out very nicely because the parameters lambda and mu just get added together. So whenever we take x and y and add them together, it becomes a Poisson lambda plus mu. To show that that is in fact the case, what we would need to show is that x plus y has the proper PMF, or in other words, that the probability x plus y equals a number k is lambda plus mu to the k over k factorial e to the minus lambda plus mu, since that's the PMF for a Poisson lambda plus mu. And the event that x plus y equals k can be rewritten as we did for the discrete random variables, as the union over all events from I equals 0 to k that x equals I and y equals k minus I. That's because Poissons are always 0 or larger, and the sum of x and y has to equal k for x plus y to equal k, of course. So x must be some number I from 0 to k, and y must be the other number that when added to x gives you k. Also, these events in the union are disjoint. So if we plug in I equals 0, we get x equals 1 and y equals k. If we plug in I equals 1, we get x equals 1 and y equals k minus 1, and so on. So they're all disjoint events. They all have different numbers for values of x and values of y. And therefore, the probability x plus y equals k, which is the probability of this event, the union from I equals 0 to k, that x equals I and y equals k minus I, is the sum. So this probability becomes a sum, since these are disjoint events, of the probabilities that x equals I and y equals k minus I. Now we use independence again, so this sum of this probabilities is the sum, the probability that x equals I times the probability y equals k minus I. And then we're going to use the PNF of x and y. So x is Poisson lambda, so the probability x is I is lambda to the I over I factorial e to the minus lambda, which is this piece here. And y is Poisson mu, so the probability y equals k minus I is mu to the k minus I divided by k minus I factorial e to the minus mu. And by just algebraically rearranging this a little bit, we can pull out the e to the minus lambda and e to the minus mu out front, and then we have the sum from 0 to k of 1 over, we have an I factorial and a k minus I factorial in the denominators, and then we have a lambda to the I and a mu to the k minus I. So what we're going to do is use the binomial theorem after multiplying and dividing by a k factorial. So taking the sum that we ended with in the previous line, we're going to multiply and divide, so dividing by a k factorial on the outside, and then I'm multiplying the k factorial on the inside of the sum, but these two things still cancel. I've just distributed the k factorial and the numerator through the sum. And then I'm using k factorial divided by I factorial times k minus I factorial is k choose I. So we have the sum from I equals 0 to k of k choose I, lambda to the I, mu to the k minus I. And by the binomial theorem, that is lambda plus mu to the k. If you're not familiar with this theorem, just go to the lesson. It's linked over here. And so therefore, we do get the proper PMF, lambda plus mu to the k over k factorial e to the lambda plus mu. And for the actuary exam, according to the most recent syllabus, for continuous random variables, you only need to know how to add two independent, normally distributed random variables. So let's let x and y be independent. Again, that's a necessary condition, independence, and normally distributed with means mu x and mu y, and variances sigma x squared and sigma y squared. Once again, we can just add the parameters. So x plus y is normally distributed with mean mu x plus mu y, and variance sigma x squared plus sigma y squared. Don't get this confused with standard deviation. You can't just add the standard deviations, because the standard deviation is the square root of the variance. So for standard deviation, we'd have to take the square root of sigma x squared plus sigma y squared. The proof is fairly complicated. We would have to use convolutions and some other things that in fact, there's even easier ways to do it, avoiding convolutions, but it's a bit more advanced material. So I'm not going to show that here, but hopefully in a later lesson.